When looking back through all of the previous 4 slides, we can see that the philosophical advantages of the ABC Preon model make it a very strong competitor in the arena of elementary particle theory. But to analyze its place in the competition, we should first list the criteria that any scientific theory must have, and then see how the ABC Preon theory meets those criteria. First, it is important that any theory be mathematically and logically correct. Second, it must be consistent with all known facts. These 2 criteria are absolutely necessary for any theory. Next come optional, strongly desired criteria. It is desirable that any theory lead to at least one testable difference between itself and its competitors. If no testable difference exists, either what is being presented is not really new, or it does not have sufficient rigor for what is a sound scientific theory. Lastly, it is highly desirable that the theory be as simple as possible. Note that the world is full of crank theories that violate all 4 of these criteria. A very frequent violation occurs in the 3rd criteria, where authors claim to be able to always derive any mass or energy value from their theory, but never predict anything new. Such theories generally also have impossible to understand underpinnings, known only to their authors, and such theories should of course be rejected. But note also that the Standard Model suffers from weaknesses on both the 3rd and 4th criteria itself. Over time, the Standard Model has evolved whenever something was discovered outside of its tenets, and the Standard Model is now anything but simple. Of course, nature may not be simple, and the Standard Model is a reasonably good map to what is known to exist, and for that reason the last 2 criteria are mentioned above as highly desired, but they are not absolute requirements. With the requirements for a good theory now listed, we can evaluate how well the ABC Preon model has met those requirements. As can be seen in the preceding presentation, the ABC Preon model is numerically and logically sound. The mathematical simplicity was introduced by the new concept of neutronic charge, with the C particle having a +3 charge and the A and B each having a charge of -1. Their antiparticles each have the opposite charge of the particles. Once those simple charges were introduced, we saw how all massive leptons can be made by a B particle being bound to an anti-A particle, and how all hadrons can be made with C particles bound to A and B particles. The second criteria is also met, since we have seen how the ABC Preon model dovetails nicely into the Standard Model. Since the ABC Preon model can be used to show how quarks and leptons are constructed, it can also construct those particles that are presently believed to be made up of those quarks and leptons. But the ABC Preon model also meets the optional criteria as well. We have seen above that the ABC Preon model predicts that a signature similar to that of the Z particle should occur somewhere around 69.6 GeV. Other predictions for new physics exist as well, as there will be similar physics to that involved in the explanation of the top quark, which was discussed earlier. Additionally, neutrino oscillations were qualitatively predicted by the model. Finally, the ABC Preon model clearly meets the desired criterion of simplicity. And in this regard, it is time to put it in its historic place by again reviewing the history of mankind's belief in what the world is made of. As we recall from the beginning of this webinar, the first model of what the world is made of was of fire, earth, air, and water in the model of the ancient Greeks. The model of the ancient Greeks required additional elements and modifications of the original elements, and eventually Mendeleev produced a periodic table of the elements with 92 basic particles making up our world. A great simplification of our view of what makes up our world was enabled by the observation that the elements of Mendeleev are themselves composed of protons, neutrons, and electrons, with each element containing a different number of those particles internally. But even at this point in time, a few additional particles were known to exist, in addition to the proton, neutron, and electron. As scientists continued to experiment with high-energy physics particle accelerators, many new particles were quickly found, leading to what was called a particle zoo, a portion of which is shown here. A great simplification was enabled by Murray-Gell-Mann's quark model, which explained the origin of some of the particles occupying the particle zoo by showing that they could be made up of precursor particles. At first there were 3 quarks along with several leptons, but as experimentation continued, additional quarks were added. This slide shows the present standard model for particle physics as advertised by its proponents. But a true picture of the standard model is more complex than what is advertised. Each quark comes in one of 3 colors, and each has an associated antiquark that also comes in one of 3 anticolors. Each lepton comes with an antilepton partner, and the strong force is believed to be carried by 8 gluons. This leaves a standard model that has 60 elementary particles within it. The next great simplification is the ABC Preon model that has been presented here, which reduces the number of elementary particles from the 60 of the standard model to just 8. It can be seen that the ABC Preon model is the next step in the pattern that has exhibited itself in mankind's searches for the answer to the question of what the world is made of. Complexity gives way to simplicity as underlying patterns in the complexity are found. The simple model then gains complexity as additional experimentation occurs until a new simple underlying pattern is found. Hence, the ABC Preon model fits proudly in as the latest example of a simplification of a previously complex model. In conclusion, you have just seen how the ABC Preon model is a scientifically correct, testable, and simple model for elementary particle physics. The scientific correctness follows from the fact that it is shown how the preons can be used to construct the quarks and leptons of the standard model, which enables the ABC Preon model to also share in the successes of the standard model. The testable nature of the ABC Preon model exists in the fact that a 69.6 GeV signature should exist in lepton and hadron colliders that is similar to the already observed 91.2 GeV peak associated with what is known to be Z particle production. Many other signatures should also exist in high-energy physics colliders associated with the production of free preon groups. The simplicity is evident in the great reduction in the needed elementary particles, as well as the reduction in the number of forces at play in the universe. As with any new theory, opportunity exists for further research. The theory should be advanced with mathematical models, and one goal should be the accurate ability to derive masses for the massive leptons and hadrons. Experimentally, verification of the 69.6 GeV signature, as well as other preon signatures, would be important confirmation of the theory. I hope you have enjoyed this presentation of the ABC Preon model, and thank you for your time.